Hello students, welcome you all to the session of solutions for heat transfer GATE 2022 subject heat transfer for mechanical engineering aspirants. So moving on to the first question. A saturated vapor at 200 degrees centigrade condenses to saturated liquid at the rate of 150 kg per second. And on the shell side of heat exchanger, enthalpy of the consideration HFG is 2400 kilojoule per kg. A fluid with Cp as 4 kilojoule per kg Kelvin enters at 100 degrees centigrade to the side tube. If the effectiveness of the heat exchanger is 0.9, the mass flow rate of the fluid in the tube side is dash kg per second in an integer. Basically, if I draw a diagram, the side of the tube has coolness Tc1, which is 100 degrees centigrade, went to Tc2, and the hot water at the inlet and the exit is Th1 is equal to Th2, which is 200 degrees centigrade, right? When we take the condition Cp as 4 kilojoule per kg Kelvin, HFG is 2400, Xi value is effectiveness 0.9. We know that Xi is Q by Q max, which is Tc2 minus Tc1 by Th1 minus Tc1, which will be Tc2 minus Tc1 is 100 by 200 minus 100. This is 0.9. From here Tc2 is equal to, when I calculate Tc2, I'll get 190 degrees centigrade. So the rate of steam condensation, m dot h is 150 kg per second. This is m dot h into HFG is equal to m dot c into Cp, T2 minus T1. This is cold temperatures. That is 150 into 2400 is equal to m dot c into 4 into 190, right? 4 into 190 minus 100. So m dot c is equal to 1000 kg per second. Mass flow rate of cold water. He is asking you the next integer 1000 kg per second will be the right answer for the given question. Right. Moving to the next question. Consider steady state one-dimensional heat conduction in an infinite slab of thickness 2L, that is L is 1 meter, shown in the figure. The conductivity K of material varies with the temperature as K equal to Ct, where T is the temperature in Kelvin, C is the constant equal to 2 Weber per meter Kelvin square. There is a uniform heat generation of 120 kilowatt per meter cube in the slab. If both faces of the slab are maintained at 600 Kelvin, the temperature at x equal to 0 is K. Simple logic. X equal to minus L, x equal to L, x equal to 0. This is the center. Heat generation will be there here. We say Q of G. This is Ti. This is the length L. This is length L. This is T2 600 Kelvin. This is T1 600 Kelvin. Conduction heat equation in this case will be d by dx of Ct d by dx plus Q dot G will be equal to 0. Integrating it, when we are integrating it, Ct dt by dx plus q dot gx is equal to c1. Again, one more time, if we integrate, ct square by 2 plus qg into x square by 2 is equal to c1x plus c2. When we are talking about the boundary conditions, x is 0, dt by dx is also 0, x is L, T equal to 600 Kelvin, right? So when you substitute back in this, what happens to C1? 0. C2 is C T1 square by 2 plus Qg into L square by 2. This is the condition which you are going to get. With the generic distribution, generally we write T square by 2 is equal to T1 square by 2 plus Qg into L square by 2C minus Qg into x square by 2c. Got it? This is into only, or else don't get confused once again. Into. Now t is equal to root of t1 square plus qg L square by c minus qg x square by c, where when x equal to 0, t equal to t max, right? So T of x equal to 0, that will be initial temperature root of 600 square plus 1280 by 2 into 10 power 3. So from here, if we calculate Ti or T1, you will get around 1000 Kelvin. That is 1000. The temperature at x equal to 0 in integer is 1000 Kelvin. This will be the right answer for the given question here. Moving to the next question. Consider a hydrodynamically thermally fully developed steady flow with 1 kg per second in a uniformly heated pipe with a diameter 0.1 meter, length 40 meter. Constant heat flux of magnitude 1500 watt per meter square is imposed on the outer surface of the pipe. The bulk mean temperature of the fluid at the entrance is 200 degrees centigrade. Reynolds number is 85,000 and Prandtl number of the fluid is 5. Thermal conductivity and the specific heat of the fluid are 0.08 watt per meter Kelvin, 2000 and 2600 joule per kg Kelvin. The correlation is Nu is equal to 0.023, Re per 0.8, Pr per 0.4, which is applicable, where the Nusselt number is defined as basis of pipe diameter. Pipe surface temperature at the exit is dash degrees centigrade. For suppose this is a pipe, mass flow rate is from here T1, TB1 or 200 degrees centigrade. Diameter is 0.1 meter. Total length is 40 meter. T2 we need, TB2 you need. Mass flow rate is 1 kg per second. Nu is equal to Hd by K, which is given as 0.023, Re per 0.8, Pr per 0.4, or H into 0.1 by K is equal to Re is 85,000 power 0.8 into 5 by 0.4. Calculate this. What you are going to get from here? You are going to get H is equal to 384.45. From there H is equal to 384.45 into 0.08 by 0.1 on solving 307.56. Heat flux Q of G is H into TSE minus entry exit. TBE, bulk exit temperature of the fluid, we call it as, right? So 15,000 307.5 to TSE minus TBE, bulk temperature at the exit. From here, on calculation, TSE minus TBE will be equal to 48.77. Now, by conservation of energy, rate of heat dissipated is equal to heat gained by the fluid, right? Q dot of G into pi into D into L is equal to MCP T2 minus T1. From here, 15,000 into pi into 0.1 into 40 is equal to 1 into 2600 into TBE minus TBI. Let it be equation 2. Got it? From here, on calculating T2 minus T1, where T2 less TB minus T1 minus TB. All values are known to you. TBI is 200 degrees. It is been given to you in the question itself. 200 degrees is given to you in the question itself. On substituting, you get TBE is equal to, from this equation number 2, 48.77, that is 72.49 plus 200, where it is 272.49 degrees centigrade. Take this and substitute in first equation. This is the first equation I wrote about. TSE minus TBE. Substitute TBE here so that you will get TSE. You should get around 321 degrees centigrade. So the answer, the pipe surface temperature at the exit is 321 degrees centigrade. Bulk at the exit is 272.49. This will be your answer for the given question. One mark question. This is next question. Which of the following non-dimensional term is an estimate of Nusselt number? Ratio of rate of which internal energy is advected to the rate of conduction heat transfer. B. Non-dimensional temperature gradient. C. Ratio of internal thermal resistance of solid to the boundary layer thermal resistance. D. Non-dimensional velocity gradient by Prandtl number. Generally, Nusselt number Nu is convective heat transfer to conductive heat transfer. Convective heat transfer to conductive heat transfer, where convection includes between both adhesion motion and diffusion. So the dimension number closely related to fluids is Rayleigh's number, which you call Nu is equal to HL by K, where it is delta Ts minus T by dy by Ts minus T infinity by L. So your Biot number is R of conduction to convection, that is convective resistance to convective resistance. So obviously for Nusselt number I can clearly say internal thermal resistance of the boundary to thermal resistance, that is option non-dimensional temperature gradient, or what you are going to get it for Nusselt number. Nusselt number will always give you a non-dimensional temperature gradient. Option B will be the right answer for the given question. Convective heat transfer to conductive heat transfer. These are the questions from heat transfer. Hope you people have understood. Thank you, students.